Good morning, everybody. Thanks for being here. It's nice to see people are back after the break. So we are happy to start the seminar for 2025. Our first speaker this morning is Alex Hall from the University of Edinburgh. So Alex did his PhD at the University of Cambridge, graduated in 2014, and has been since at the University of Edinburgh as Royal Society University Research Fellow. And he is also one of the co-leads of the Weak Lensing Science Working Groups in the Euclid Consortium. And that's the subject of the talk this morning, Weak Lensing Cosmology with Euclid. You have the floor for the next 45, 50 minutes. Thank you for being here.
Thank you very much, Laurent. And thank you for the kind invitation. It's a great pleasure to be here today and give this seminar. So I'm going to talk about weak lensing cosmology with Euclid. I won't be able to actually show you any weak lensing cosmology results from Euclid, of course, but I can at least talk to you about the state of this field and the efforts that are ongoing, both in the Euclid Consortium and elsewhere, to tackle some of the big challenges that we face in this field. Okay, so just the plan of this talk. I'm going to start by motivating all of this. I know that this is quite a diverse audience. Lots of experts in cosmology, lots of experts in Euclid, but also people from different fields. So I'm going to just try to convince you that this is worth staying awake for. And then I'm going to introduce the telescope, talk about how we actually use the images from Euclid to do cosmology, talk about some of the challenges and some of the solutions and some of the progress that's been made in the last few years to tackle some of these challenges, and then finally just look towards the future. Okay, but let's start off at a fairly gentle pace. So we'll start off with, the concordance model of cosmology says we've got the Big Bang model. We've got several epochs of the universe that are not well understood. So if we start at the beginning, the Big Bang inflation is not, of course, well understood or even established beyond all possible doubt. We have the switch on of the first stars and the creation of the first galaxies, the reionization of the universe, the expansion of the universe, continuing, and then at this epoch here, you see the flaring out of this space-time picture, and that means the universe is accelerating in its expansion, which we attribute to dark energy, which of course is not really well understood at all. So there's lots of challenges here, but we do have a model that seems to describe this physical picture very accurately, at least on large scales. And that's the Lambda CDM model. Okay, it's one of the great success stories of cosmology over the last few decades. And in the Lambda CDM model, we have these constituents. Okay, let's just look at some of these. So perhaps the biggest kind of uncertainty is this one. This is lambda, dark energy. It's the thing we put into our models to explain the acceleration of the universe. So what is this? Is it some new fluid? Is it some manifestation of a modification to the laws of gravity? Is it some new scalar field? Of course, this makes up 70% of the universe energy density today. And the far future of our universe is one in which dark energy is the dominant component. What do we understand about this? Well, we know that if dark energy really is a fluid, it should be very close to a cosmological constant. We can quantify that with the equation of state parameter, W, for dark energy. -1 refers to a cosmological constant. These are constraints from last year from the DESI collaboration, showing you various different probes, constraints in the omega matter, the matter density, this part, and the dark energy equation of state. And you can see that when you combine all of these things together, CMB, the baryon acoustic oscillations from galaxy surveys, supernovae, you end up with this small orange contour here, which is aligned perfectly with the horizontal line. So it seems that dark energy is very close to lambda. But of course, if you have some time dependence, if you assume that the equation of state could vary with time, there are these intriguing hints of something more interesting going on. So in this parameterization, the equation of state, W, which is the ratio of the pressure to the energy density of dark energy, if we give it a kind of simple linear dependence with the scale factor, so W naught is its value today, then constraints actually are pushed away from the lambda CDM prediction, which is the where the crosshairs meet here. So this is results from the DESI galaxy survey from last year, combined with CMB and supernovae. And there's ongoing debate about the significance of this result and possible systematics in the supernovae samples. But there's intriguing hints that maybe there is evidence for dynamical dark energy. Cold dark matter, again, another major constituent of the model that's poorly understood. What is it? Is it a new particle? Is that particle self-interacting? What is its coupling to the standard model, if any? We know some things about this. We know that dark matter is cold. In other words, we can put a lower limit on the mass of a potential warm dark matter component. 3 keV is the current best lower limit. The significance of that is unclear. Of course, people have now considered many other models for dark matter, including these very ultralight axion models. Masses here 10 to the minus 29, 28 electron volts. These are the constraints on what fraction of the total dark matter could be in these ultralight axions. And you can see the limits are sort of 10%. Maybe you can get more with these heavier masses. But again, this is it's a poorly understood component of the model. Neutrinos are part of this story. Neutrino is another important constituent of the energy density in the universe. And one of the kind of problems or outstanding uncertainties in particle physics is what is the total mass of the neutrino. Particle physics tells us what the differences of the squared masses are, okay, but it doesn't tell us the total mass. So cosmology is an area where we can actually measure, we're actually sensitive to the total mass because we're sensitive to the total energy content of the universe. And again, these are latest constraints from DESI showing the sort of allowed probability distribution. These are Bayesian posteriors of the total mass. And you can see that we're putting upper limits on the total mass of order 0.1 electron volts. This is starting to get interesting because if you take these particle physics constraints, this really kind of delineates two possible orderings of the neutrino masses. And each of those orderings has a minimal mass corresponding to one of those neutrinos having zero mass. And those two minimal masses for the two hierarchies, we call them normal and inverted hierarchies. These are the vertical lines here. And you can see that the constraints are now starting to essentially exclude the inverted hierarchy by demanding that the total mass is lower than that 0.1 eV. But this is model dependent. If you allow the dark energy sector to be something more flexible than lambda, constraints broaden. Also, it's kind of intriguing that these constraints are not peaking around the minimal mass of the normal hierarchy. Okay. Baryons, okay, I'm not going to talk about this, but I mean, we're meant to understand these, but we don't really, because we don't understand the origin of the matter-antimatter asymmetry in the early universe. And of course, there's a whole set of open problems in the formation and evolution of galaxies and reionization and questions in the late universe. So these are the components of the universe. These are the constituents. Of course, in our model, lambda CDM says that there is some set of initial conditions. Gravity is the major force acting on large scales. Initial conditions, what are the problems there? So here we're talking about things like inflation, the early universe. What do we think we know about inflation? Did it really happen? If so, how? Here I'm showing constraints on parameters that govern the initial conditions of the universe. This is from CMB. CMB constraints. So on the vertical axis, I'm showing the possible amplitude of a primordial gravitational wave component that might be expected from inflation. On the horizontal axis is the slope of the initial fluctuations, the initial spectrum of fluctuations. And various predictions from models are shown in these solid lines. And the best constraints are the blue contours. These are models for single fields inflation that has a potential given by a simple kind of monomial or simple power law. And actually, the constraints are now ruling out these monomial models entirely. So the simplest models for inflation are seemingly ruled out by these constraints. So I've already mentioned the possibility that dark energy or the acceleration is actually a manifestation of modified gravity. So we can test this. Again, cosmology is a really great way of testing extensions to fundamental physics. So one of the kind of popular extensions people like to look at is the gravity sector. So we can do this by essentially saying, what if Newton's constant evolves with time? What if there's some, fancy new physics in the gravity sector? And these are the constraints. This is a combination of weak lensing and galaxy surveys in gray here. GR would be 0, 0 on this plot just here. And you can see there's no evidence for modified gravity. But this is, again, something we'd like to understand better. These parameters are constrained at the kind of tens of % level. We'd like to do much better than this. All these come together with the laws of physics, conservation laws, dynamics, and predict our observables. Okay, so that's the Lambda CDM picture. There's lots of open questions there. Something else that's really kind of popped up in the last few years is this idea of cosmic tensions. Okay, and what I mean by that is that different probes can have different ways of measuring the cosmological parameters, the components of the Lambda CDM model, and they should all agree, right? If the model is correct, you can look at things in different ways, and they should all agree. And of course, they don't agree. And the biggest issue in this area is the Hubble constant. There are discrepancies in the value of H naught, the present expansion rate of the universe, between direct measurements in the local universe, the classical distance ladder measurements, where you take supernovae calibrated with Cepheids. Okay, those give a high value of H naught. You can also measure H naught with large-scale structure and cosmology and the CMB by looking at the distances to the CMB. We think we know from early universe physics or well-established physics that the CMB has a preferred physical scale. We can measure angular features in the CMB so we can get a handle on the distance. So that tells us H naught. Those measurements give a lower result. So the CMB measurements are shown in this very pale pink band that you probably can't see at the back. And the distance ladder measurements are in the green band. This is a huge, 5 sigma plus discrepancy. This is not understood. So there's a lot of work ongoing to understand this. And new data from JWST is hopefully going to shrink some of these error bars, and we'll either push this band left, or it will just shrink the error bar, and perhaps the CMB. There'll be further improvements in that measurement too. The other sort of tension, this is a less significant tension. It's called the S8 tension. S8 is this funny parameter that's a combination of these two parameters. So sigma 8 is a parameter that controls how lumpy is the universe? What's the kind of typical variance of fluctuations in the mass on a scale of 8 co-moving H inverse megaparsecs? Okay, just a kind of conventional scale that defines this parameter. Multiplied by omega matter to the 0.5 power. This is just a particular combination of parameters that low redshift structure formation surveys are sensitive to. So it's roughly speaking the amplitude of the weak lensing power spectrum. So this is something that you can measure almost directly with low redshift probes of large scale structure, but it's also something you can measure indirectly by looking at the amplitude of fluctuations in the CMB and then extrapolating them down to the same redshift down to low redshift, down to rate of 0, essentially. That's model dependent, of course, because if you're doing that extrapolation, you need some model for how structure is meant to grow between redshift 1000 and redshift 0. But if you do that, you find some intriguing discrepancies. So this is a lot of constraints. This is the S8 parameter. Okay, Planck, so CMB measurement in red, and then these kind of lensing surveys giving these open contours here. Now, it doesn't look very significant, right? It looks like maybe 1 or 2 sigma. But the intriguing thing is when you start to look at lots of different combinations of probes that are all measuring this low redshift structure amplitude in different ways. So this is a compilation of such measurements from Farron et al. From last year. We can see, let's look at these red points, right? This is the cross correlation of CMB lensing with things like the galaxy density from the Dark Energy Survey. Okay, so there's no lens, there's no galaxy lensing in this. You can see the S8 constraint it's low compared to Planck. Okay. And again, if you look at, add in weak lensing, you see again it's pushed even lower. It's not a consistent picture because depending on what data set you use, you can get different results. But what's sort of intriguing is that a lot of these different combinations are giving low, like comparatively low measurements of the amplitude of clustering compared to the CMB, what the CMB would predict. Just to see that sort of more visually, like this is a kind of way of visualizing the amplitude of structure and how it's been growing with time. So in black, the black curve here is the prediction from Planck. Okay, essentially 0 error bars here. And the different points here are various different low redshift or even sort of moving towards higher redshift measurements of the amplitude of clustering at the redshift at which the galaxies in these various samples live. The Dark Energy Survey, which is the largest weak lensing survey that we currently have, the constraints are shown in the purple triangles, and this is the S8 tension. You see that it's sitting consistently below the prediction from Planck. But you see other surveys are finding these green points are low here. I mean, the error bars are large. What we'd like to do is populate this diagram with sort of more points with smaller error bars to try to understand this and try to understand that this is a signature of new physics. Perhaps there's something strange going on with the growth rate around here. Or perhaps this is a sign that the lensing and the clustering measurements are not fully understood. So how do we make progress? Okay, so I've talked to you about kind of long-standing problems with lambda CDM. I've talked to you about more recent problems or tensions. So what's the way forward here? Well, we're kind of at a really exciting moment in cosmology because we've got lots of new surveys coming online, covering lots of different wavelengths and giving you different angles, different aspects of the universe. So there's lots of probes that we can use, and a combination of all these probes is a very consistent, is a very powerful way of learning more. So we've got things like CMB, all the CMB secondaries that come in from the interaction of those CMB photons with large-scale structure at low redshift. Of course, we've got probes of the geometry. We've got gaseous traces, cluster abundances. The ones I'll be talking about in this talk are weak lensing and galaxy clustering. But there's lots of alternative methods as well to try to that all bring different sensitivities to different aspects of the model. Some of these are good for geometry, some of them are good for structure, some of them are good for small scales. They all have different systematics, of course. A lot of these are complementary. You can measure the same structure with different probes, and it's a really powerful way of nulling out systematics that might be inherent in any one probe. So I think the future is really kind of leveraging the complementarity and the kind of distinct power of all of these different probes. So I'm going to be talking about weak lensing and galaxy clustering. These are weak lensing is a relatively new area of cosmology. It's 25 years now since it was first detected. But this is sort of maturing rapidly into a probe of precision cosmology. And this experiment, Euclid, is really at the forefront of this. So I know there's lots of Euclid experts here. It's one of the main places in the world for Euclid. But there's also people in the room who don't know so much about it. So the Euclid people can sort of take a break for a few seconds. So Euclid, what is it? It's a European Space Agency space telescope, launched last year. July 2023. Stands about 4.7 meters tall. There it is in the lab. That's me for scale. Weighs about 2 tons. Well, 500 million euros cost, but I think if you add in all the extra staff costs and everything, it probably gets closer to €1 billion. It's a 1.2 meter diameter primary mirror, and there are 2 cameras on board. Okay, one for visible light and one for near infrared light. Here's the launch. just going to show it because it's really cool. July 2023, SpaceX Falcon 9.
This is less cool now, though, after...
Yeah.
It's pretty cool when we were there.
It was pretty cool back then. So I think this was, quite a kind of stressful time for a lot of people.
The funny thing is that everybody went away after the launch before it actually separated from the booster, right? So we thought, okay, it's okay, we can go. But there was only people left were the only people were the Euclid people watching the launch because everyone else had thought, okay, it's over.
Yeah. And there was a really heart in mouth minute where they were trying to establish communications with it and nothing was happening. So it was suddenly this what's going on?
This mission that is coming up here just a few.
So this is the I thought I'd show this as well because I think this usually gets a kind of gasp of excitement from a lot of audiences. This is showing the lower half of the rocket falling back down to Earth. I say falling.
Amandine, yes, it was very hard. I was next to Amandine as well.
So this is being steered down. I don't know how this is done really. I mean, gyroscopes, I suppose. Essentially like steering a stick kind of down through the hemisphere to land on this sixpence here. So yeah, there it is. It's very cool.
The story about why they didn't want to put the decal Euclid on the launcher is because it was very hard to clean it off the booster for the next customer.
There we go. Right, okay. So a bit of technical detail. There's two cameras on board, VIS and NISP. VIS is optical visible light, NISP is near-infrared light. These are very high resolution cameras. The pixel scale is 0.1 of an arc second. Very wide field of view as well, as we'll see. So kind of 0.7 by 0.8 degrees. So these are kind of purpose built for the science case of Euclid, which is weak gravitational lensing and clustering. So the lensing part, you really need very accurate shapes to do weak lensing. So you need you need to be in space, ideally, and you need this very high resolution. And the wide field of view gives you, the ability to do a very large survey. NISP has 3 bands on board, plus 2 grisms for spectroscopy. So that's going to give us, spectroscopic redshifts for a large sample of galaxies, as well as photometry for photometric redshifts. So here's the kind of wavelength range of the 2 instruments. You see VIS covers this very broad optical band, and here you see the wavelength coverage of the near-infrared channel. And Euclid is going to be conducting a wide survey and a deep survey. So the wide survey is eventually going to cover almost the entire accessible extragalactic sky. This is just a plot from a paper I will be referencing a lot in this talk, which is the Euclid overview paper from the archive last year, from Melier et al. So this is showing the survey as a function of time. So we kind of build up area in the north and the south. And then by the end of the survey, which takes about 6 years, we have this very large area that is about 15,000 square degrees. Okay, down to a limiting magnitude of around 24.5 VIS. Okay, it's kind of a wide and deep survey. So first, soon after the telescope was launched, we got the first commissioning images down, and this just gives you an idea of the size of the field of view. So the full moon for scale, HST, ACS field of view for scale as well. As you can see, we're getting a big patch of the sky with every exposure. Okay. But also exquisite resolution. So this is these are huge images. If we just focus on a little section of this, this is quite a raw image. You can't see this so well with the contrast, but you see like interesting things popping out. So you see edge-on galaxies, spiral galaxies, cosmic rays. So Henry and the OU-Viz team are doing absolutely brilliant work to kind of understand these images and process them and prepare them for kind of all the cool cosmology that we want to do with them. So we do a wide survey, we do a deep survey as well, where we go 2 orders of magnitude deeper in a few deep fields. But yeah, we do a third of the sky over the next 6 years. That will end up being a catalogue of about 1.5 billion galaxies. And that catalogue will have excellent shape measurements, photometric redshifts, lots of other morphological parameters, and lots of more information about this sample. We get 35 million galaxies with spectroscopic distances as well. So this is a huge resource for all of astronomy, not just cosmology. So there's lots of other non-cosmological science that benefits from a data set like this. And the strategy that we take is to sort of just build up areas slowly. So this is quite a different strategy to say the Rubin LSST survey, which kind of builds up depth. We build up area. So we kind of eventually we purposefully avoid the Milky Way plane. We don't look there, and we avoid the zodiacal plane as well. So we're kind of avoiding these dusty areas. Okay, I don't need to spend much time on this because your department is kind of peppered with these beautiful images on the walls. But just a few kind of highlights from the early release observations from Euclid. This is the Perseus cluster, just very, very, very impressive. And there's a nice kind of illustration of the power of Euclid versus ground-based surveys. This is an image of Perseus from the Digital Sky Survey. And if we overlap the Euclid image, you see that we get a much wider field of view, we get high resolution, we get depth. So this is sort of an illustration of the power of this. And I like this one as well. This is the hidden galaxy. It's a big galaxy that you get very nice images in the near infrared. It's quite close to the Milky Way plane. It's one of the largest galaxies on the sky in terms of angular size. But it's quite hard to see from Earth due to its position on the sky. But you get this very nice image with Euclid. Horsehead Nebula, again, you can actually just about see the filamentary structure in the H-alpha emission caused by magnetic fields. There's a Scottish connection to this, which I always push whenever I give this talk, which is that this is credited, the discovery of this object is credited to Wilhelmina Fleming, who was Scottish, born in Dundee in 1888. So I just had to put that out there.
She observed that where?
She was analysing Harvard Observatory plates.
Not in Scotland.
Not in Scotland, no. No chance you'd see it from Scotland. So timeline for Euclid, we're about here. We're a few days away from a major data release on the 19th of March. This is a sort of small data release, the Q1 release. And then the ESA website says that there'll be a DR1, our first big patch of sky, our first big cosmology survey released in 21st of October 2026, okay? And then we'll have these kind of regular data releases, DR1, DR2, DR3, as well as these intermediate smaller releases over the next sort of 5, 6, 7 years, okay? So the core science is gravitational lensing and galactic clustering. So that's what I'm going to spend the rest of the talk on. So weak lensing, it's the statistical alignments of galaxy shapes. So you take a bunch of images, you measure the shapes, and you look for these correlations in the alignments, and that is meant to be due to gravitational lensing. There's an extreme example of this here. This is a strong lensing system, so you can't really see it so well, but there are these kind of arcs, right? These are strong lensing arcs. But essentially, you're seeing some coherence in the shapes of galaxies caused by gravitational lensing. So that's the effect we're trying to look for. But we can also do galactic clustering, just measuring the angular and radial positions of our galaxies, and we see large-scale structure just popping out. This is a plot from Vipers showing a chunk of the universe. You can see the structure popping out. So these are sensitive probes of cosmology. It tells you about the structure at any given time, so the kind of distribution, which is telling you something about the initial conditions and the sort of and the physics of of galaxy clustering. But you can also look at this as a function of time, and it tells you about how structure is growing and evolving, and that's sensitive to things like dark energy, which will cause gravitational potentials to decay on large scales. So just to give you an idea of the size of this effect, weak lensing, it was only discovered 25 years ago because it's a very weak effect, right? Imagine you've got a galaxy at redshift 1. Okay, the RMS deflection angle for a galaxy at that redshift is quite large, 1 arc-minute. But we're sensitive to the distortions of galaxies, which is the gradient, the deflection angle on the scale of a galaxy. And that's typically around 1%, or even less, 10 to the minus 3, depending on the scales we're talking about. There's a very, very kind of subtle change in the shape of a galaxy due to lensing. But the thing that allows us to measure this is the fact that this is correlated over degree scales. So there are large-scale correlations in the shapes of galaxies. Just illustrated here, where we've got, imagine you put a blob of matter in front of a lot of circles, lens them, you see ellipticities emerge, but you see correlations, right? You see this characteristic pattern that's due to lensing. The way this works in practice, okay, we want to measure shapes. It's difficult because lots of things can affect the shape of a galaxy, not just lensing. So as well as the lensing itself, we have sort of blurring out by the optics of the telescope. We've got the impact of the detector and the noise. So, in practice, I mean, this is a kind of a good example. Most of the galaxies are a lot smaller than this, but this shows you, the challenges, the practical challenges faced when trying to measure the shape of a galaxy to such accuracy. And because we're stacking essentially millions, hundreds of millions of galaxies in Euclid, we have very tight requirements on the systematic biases, okay? So we have to measure this with an overall accuracy of about 0.2%. So this is it's kind of far beyond what any lensing survey has tried to do in the past. Once we have all those shapes, what we do with them, well, we like to compress them into summary statistics. This is the traditional way that we've fit models to weak lensing. So we do things like the correlation function, looking for correlations between ellipticities on large scales. So this is showing the kind of current state of the art for the weak lensing correlation functions. So these 3 panels show 3 different current weak lensing surveys. So we've got the kilodegree survey over 1,000 square degrees in blue. Okay, the best fit model is in black. Here we've got the dark energy survey year 3 results in pink. And this is the HyperSuPrime year 3 constraints in orange. So you can see the Euclid forecast errors. You can't even see the error bars here because they're comparable to the size of the points. So if all goes to plan, our statistical constraining power is, it's far beyond what current surveys are achieving. There will be new releases of KIDS and DES this year, so you should watch out for those.
What's the origin of why does it turn over in the middle? I don't understand that.
It's theta times the function.
Okay.
Yeah, there's a factor of theta here just to make things, put things on dynamical scale. But you actually start to see the effects of the matter radiation equality scale in the matter power spectrum. This is the typical range of redshift that we'll get with Euclid. We've got a photometric imaging survey here. We rely on ground-based surveys to provide the fluxes to get us those redshifts. We can't just rely on the Euclid bands. So we'll get galaxies out to redshifts of 2 or 2.5, but sort of peaking at around redshift 1. So there's tight requirements on understanding where the galaxies are. If you take a bunch of galaxies and try to fit their weak lensing signal, you've got to know how far away they are, because how far away they are impacts the predicted lensing signal. So you need to have a very accurate understanding of the true redshift distribution based on noisy photometry, which is a very challenging problem. So there's dedicated spectroscopic training samples under construction to meet these requirements. Yeah.
Up to which redshift is considered to be complete the survey for a given magnitude?
Yeah, so for weak lensing, we're not so much interested in completeness, because we're just measuring like shapes of galaxies rather than counting galaxies. But for the clustering aspect of this, incompleteness. Again, it doesn't matter so much for the photometric survey. For the spectroscopic survey, it's targeting actually between 1 and 2. So this is the reason where I don't know the exact numbers for the completeness of that survey, but it'll be in the Mellier et al. Paper. And just for kind of to compare this, to put this try to understand the context of the Euclid surveys with this compared to current surveys. You know, this is a plot from Angus Wright's paper last year, showing where different imaging surveys lie on a plot of area versus number density. Okay, so these are deep surveys and these are wide surveys. So these surveys here are what we call the stage 2 and the stage 3 surveys. So dark energy survey, KIDS. Euclid's right up in the top right here. Okay. You also see the next generation of the stage 4 surveys, Nancy Greater Roman, the NASA telescope, covering deeper but potentially not as wide. LSST, Chinese space station. Lots of information on here as well. You see the PSF and the different wavelength coverage. So these contours show you the total number of galaxies, right? And so we're right up here in the kind of 1 billion plus region. So this is where we are now. And this is where we're moving to in the next 5 years, right? So it's an absolute order of magnitude increase in terms of the total number. So there's lots of challenges that this presents, because with this great statistical constraining power becomes sensitivity to uncertainties in the modeling and uncertainties in the calibration that weren't as extreme before. This is a plot from the Dark Energy Survey Year 3 weak lensing paper showing actually we're already at this junction in cosmology where we're starting to be limited by our modeling, okay, and our ability to really model this signal. And for weak lensing, the main challenges are in understanding the matter distribution on small scales and the intrinsic alignments, okay? Galaxies like to align with each other or large scale over densities, even in the absence of lensing. So that's a contaminant. So if you look at the constraints on S8 and omega matter from the Dark Energy Survey, and you just say, well, imagine we knew the IA, the intrinsic alignments perfectly. Imagine we had a perfect understanding of the baryon feedback and the small scale physics. What constraints would we get? Well, that's the red contours. So you can see there's a significant increase in constraining power that just comes from, or to flip it around, a significant drop in constraining power due to the not understanding the nonlinearity in the signal and the modeling challenges. So as well as that, as I've already said, we need to accurately understand the redshift distributions. We have tight requirements on the uncertainty of the mean of those N of Z's. Of course, we need to understand what the PSF is doing. We need to more generally understand the measurement process itself and the biases that can arise. And this is something that I've kind of worked on quite a bit in the last few years. So just to sort of pick out one of these challenges, so this is baryon feedback is one of the main challenges for weak lensing. So this is showing predictions for the matter power spectrum. Weak lensing is very sensitive to this matter power spectrum as a function of scale. So this is these are large spatial scales over here. This is the Fourier wave number. Large spatial scales here, small spatial scales on the right. And these are predictions from various hydrodynamic simulations. Okay, this is the ratio of the matter power spectrum to the dark matter only or gravity only prediction. So this is showing you the impact of baryon feedback. So AGN blowing gas out around, the gas moves the dark matter around and changes the weak lensing signal. So these are large corrections to the signal at the kind of 10% level, and they become dominant at very small scales. But what's kind of what you can see is that different simulations predict different things. There's a wide scatter in the possible forms of the baryon feedback. So we really don't understand which of these curves, if any, is correct. Depends on subgrid physics and the details of baryon feedback. So if we want to use those small scales to do cosmology, and we have very accurate measurements of those small scales, we better make sure that we're not vulnerable to models of baryon feedback that are not flexible enough. Okay. Just to show what this can do to parameter constraints, this is work from our student, Edinburgh, Alex Morau, showing shifts in the omega matter sigma rate plane as you go to smaller and smaller scales. The different colors here are including smaller and smaller scales. So the red contours is using a very conservative cut on scales, using only the largest angular scales, where you're really only sensitive to the very lowest Ks here. So that's where you're basically throwing away big chunk of data. Including smaller scales biases you significantly, right? You get pushed out away from the fiducial value. And yeah, just to advertise some of his work, then he's explored this theory uncertainty method where you try to add in some extra uncertainty into your covariance matrix to try to mitigate this. And yeah, this paper shows that it works very nicely. So you can go from a situation where you have an inflexible model for baryon feedback, where your constraints are all over the place, okay, corresponding to those different hydrosims. But by including the uncertainty amongst those hydrosims, you expand it, you blow up error bars a little bit, but you end up being unbiased. So it's a kind of general method that seems to work quite nicely. Something else that we kind of have been worrying about is higher order weak lensing effects. So there's, this is where the talk's going to start to get a little bit more technical, but there are effects like source lens clustering, magnification bias, source obscuration. So these are effects which are really kind of almost unique to weak lensing, with the fact that we're measuring weak lensing at the positions of galaxies, and the galaxies themselves are tracing over densities. So there's like higher order effect there. This is a plot from a Euclid paper from last year, Deshpande et al., showing the corrections, the fractional corrections to the weak lensing power spectrum as a function of angular scale. Red is the cosmic variance. That's the kind of best uncertainty that you could ever get. And these effects start to become greater than cosmic variance at L's of 1,000 or so, the exact scales that we're trying to target with surveys like Euclid. And actually, you see big cancellations between these effects. So we're now having to worry about these kind of higher order effects that previously could be ignored safely. Something else that I've been working on in the last few years has been the power spectrum estimator. So this is sort of becoming the most popular estimator for weak lensing. Been very, very commonly used in the CMB for many years, of course. So we have challenges, not unique to lensing, but there are kind of strange there are unique angles of this in weak lensing. Things like the distribution of the CLs. We're doing a Bayesian inference, so we need to write down a likelihood function. That likelihood function is non-Gaussian on the largest scales, so scales comparable to the survey. So again, we've been looking at non-Gaussianity in the likelihood, how it impacts with nonlinearity in the signal. So related to the question of whether you should vary cosmology in your covariance matrix in your MCMC chains. It's an interesting question that is sort of covered by this work. So if you're interested in that, you can go and read that paper. More recently, this is work with Nicolas Tesoro, who's led the power spectrum estimation in Euclid. So we've been sort of looking into pixelization effects and window function effects. So with Euclid, we have a large sky survey. We're using power spectra to essentially bin shapes in pixels and then run heel picks to get the power spectrum. So we can be sensitive to the window function for the pixels. This is a map showing the variation of the pixel window function over the sky in the heel pix pixelization. So we're actually sensitive to the percent level to variations in the window function. So if you've got surveys that only cover, let's say you've oriented your grid such that your survey is living in this polar region, then you see quite pronounced variations in the window function, which give you percent level corrections. So you can define kind of bespoke pixel window functions by kind of confining this to the survey footprint. So again, if you're interested in any of this, this is a long paper that we put out last month that kind of dives into this. Again, like we're making a lot of use of pseudo CLs in Euclid at the moment. It's it's one of our most developed estimators, and so there are well-known issues with the pseudo CLs. It's known to be suboptimal, even for Gaussian fields, especially on large scales. So And Alex, our student, a couple of years ago, looked into this and kind of quantified how much information is being lost here. The pseudo-CLs are close to optimal, but you can get 20% improvements on large angular scales and much more significant improvements in the B mode. Okay, so there are kind of more optimal methods that know, for example, that lensing doesn't produce a B mode, so have kind of a more sensible weighting for the maps. So you get quite significant improvements in the statistical uncertainty of the B mode on large scales, where large scales here means comparable to the footprint. Okay, just in the last kind of minute or so, just another kind of bit of ongoing work. So I sort of mentioned the spectroscopic sample in Euclid. This is a higher redshift sample between redshifts of 1 and 2. So it's kind of typically higher redshift than the sources that we use for lensing. But we are actually able to measure the galaxy-galaxy lensing signal of the background sources around those spectroscopic galaxies. This is a plot from Mellier et al. Showing the predicted signal to noise in various redshift bins. So we're using the so we measured the redshifts by the H alpha line. Just said that. So that's these are emission line galaxies. So we can use those as lenses, and then we measure the correlated shapes around those galaxies. Okay, and we should get pretty significant signal to noise on those. And actually, this is quite complementary to the standard 3x2 point measurement. So this is showing kind of just a very simple forecast with Hironao Miyatake showing this kind of high redshift 3x2 point using the H alpha sample as lenses combined with the low redshift 3x2 point. And it's quite it's broader errors, but it's orthogonal in this W0 Unger matter space. It's quite nice. So we're going to get, well, if all goes to plan, we'll get very tight constraints on W0 WA and on omega matter sigma 8. So just forecasts from a couple of years ago for Euclid just showing you a combination of all our probes, all the cross correlations. We're getting this very, very tight little error bar here. This is the current state of the art here, omega matter sigma 8. Broad constraints. You see this slight S8 tension thing here. Okay, Planck and lensing. So the hope is that by DR3, Euclid will be this tiny little contour in there. Shed some light on this issue. But of course, W0 WA is our kind of main target here. So this is a forecast again from Mellier et al. Showing what we're aiming for with W0 WA. It's this purple contour here. So it's a few percent level constraints on W0 and 10% level constraints on WA. So you think, well, why is this interesting? This is quite a nice, simple argument, which I've seen Eric Linder discuss. So this is saying, well, if you imagine you've got this simple model for the dark energy equation of states, a linear model, you think, well, what are the natural values for the time dependence of W? You think, well, either it's 0, which is just lambda, or it's somehow connected to the overall expansion rate, right? That's the other natural time scale in the universe. So the Hubble parameter, that corresponds to a W primed of either 0 or 1, okay, W primed derivative with respect to the scale factor. So if you want to distinguish those two at 5 sigma, you need sigma WA of 0.2, okay, which is about what we're getting with DR3. So this should give us, it should be able to sort of rule out natural models, if you like, natural models of quintessence, for example. So just to sort of summarize, so our end goals are to measure dark energy properties at the percent level, answer these questions like, is dark energy evolving? Is it static? We're going to test GR. We're going to try to measure the mass of the neutrino. We'll be able to say something about the initial conditions because we're going to get these really high signal to noise measurements of the spectrum of structure. So we'll be able to say, were the initial conditions more complicated than we currently think? We'll do this by looking at this chunk of the universe, following this epoch where the universe starts to begin its acceleration. So we'll sort of track this epoch. We'll look at the effects of dark energy domination on these maps of dark matter and galaxies. And this is going to take place, in the next 5 or 6 years, surveying almost the whole accessible extragalactic sky, over 1 billion shapes and positions. We'll make these big dark matter maps, rule out natural models, hopefully, and yeah, just to finish, look out for the Euclid Q1 release on the 19th of March. So thank you very much.
you very much, Alex. Are there questions in the room? Yes, please.
If we plan to follow up, especially galaxies which are strongly lensed, for instance, is radio?
Yeah. I mean, one of the great things with Euclid is will provide a huge sample for follow-up observations. Yeah. So strong lensing, it's really good for finding strong lenses. There's if you look at forecasts, we'll find hundreds of thousands of galaxy-scale strong lenses, and so yes, spectroscopic follow-ups. Yeah, absolutely. Going to be it's going to be very rewarding. Yeah.
When you were showing the slide on the effect of different hydrodynamical model, so you had like a bunch of slides, but one of the first is like when you go to high L, basically it shifts the inference, but you were comparing what, like a one hydro model to another, or you were doing tests on, I didn't follow that part.
Yeah, that's like the bias from assuming a model for baryon feedback that is not able to capture any a specific baryon hydrosim prediction. So it's like, what's the bias from if the real universe looks like one of those hydrosims, but we use a model like an HM code model used in the past, what's the resulting bias?
Following on this question, so the plan nowadays is to calibrate using simulation results, your bias model, or to derive it from observation somehow.
Personally, I think the way forward is to use. So we need flexible models. So we need models that have sufficient freedom to capture plausible feedback scenarios. And then we'll probably need to rely on other observations to calibrate those free parameters, such as kinetic SZ, X-rays, perhaps other complementary observations that can pin them down. Yeah.
So as a follow-up, actually, what did you use to build your extra covariance?
So we looked at the scatter in those simulations, and we basically just parameterized that scatter in a simple kind of...
Yes, with just the envelope. If I can just put a little bit of our advertisement, there was a nice paper by Pranjal Rajendrasim, with whom I worked a while ago, and doing similar things with essentially PCA modeling of the, instead of what you're using, trying to find a model to capture all of the possible bionic effect, just using a PCA approach. It works really well as well.
Yeah.
You're marginalizing over a few parameters, and you don't have to burst up your...
Yeah. I'd say this method is our method is more, it's throwing away more, I'd say. Yeah, but yeah, you're quite right.
It was very nice.
Henry?
Thanks very much for the nice talk. I liked how all of the uncertainties related to the instrument and knowledge of the PSF was completely glossed over in your talk. Can you comment on I was just wondering, the stuff related to the higher order effects that need to be correctly addressed, like the magnification bias and all of these things. Has the budget for that changed since before the mission, like over the last 10 years? Are those effects more important now or less important? How are they important are they compared to the other sources of uncertainty, for instance, in the model for the instrument?
They are less important than that. And that particular paper I was referencing there is all DR3 levels sensitivity. And one of the results is actually there's cancellations as well. So I would say the significance is that, if anything, it's less important than it was, but it's almost an accident because of the cancellations.
Because at the start, everybody was worrying all the time about intrinsic alignments, but it seems to be less important now than it was at the start.
I wouldn't say it was less important.
Okay.
I wouldn't say it was less.
Just we have other problems.
Okay.
Last one, going back to your first slides about tension. So assuming we assuming everything goes to plan, and if it's perfect, so it's going to go according to plan, we possibly will have a large tension. Have you tried to compute how much it's going to be if you just scale the Planck result when ACT soon, SPT soon, we'll get error bars which are compatible with Planck, so we can expect a shrink by a factor 2. Let's assume that they'll get the same sigma 8. Where are we going to be on Euclid? That's the first part of my question. And the second part of my question is that, as you showed, measurement of galaxy clustering and photometric redshift and shear, all of that, there are lots of, and of course, bionic feedback, there's lots of challenges. What if we were to descope all of that? Will we still have a significant tension? I guess so, and how much is going to be? So what is the problem in front of us if Euclid ends up getting the same result as kids and DES with better error bars?
Yeah. So on the first part of your question, imagine that we do meet this optimistic forecast, and we're in this little contour here, which is extending from 0.32 out to maybe 0.325 or something. And if we look at on this, there's 0.35. So I think we're like here, right?
Yeah.
So maybe you could say, well, if that shrinks, I don't know how much that's going to shrink. Factor 2, say, you could be looking at 5 sigma easily. Yeah. In terms of the challenges, yeah, I mean, there's been a lot of work trying to understand where this tension is coming from in terms of scales and redshifts. There's some hints that it's really being driven by the small scales. One of the good things about Euclid is it's a full sky survey, or will be. So for the first time, we'll get measurements of very large angular scales. So you think, well, maybe we can just try to do conservative scale cuts and just use the linear scales that we think we understand. Then who knows? The error bar is going to blow up, but maybe it's going to move. It's all linked to this question of what the small scales are doing.
Those pesky galaxies.
Yeah, I wish they weren't there.
Cindy is getting there as well. So.
Yeah.
More question? Right. No, thank you very much again. Thank you.